So you guys gone to a break and came back. Any questions you think you came up with after you thought about it? Is everything clear? The trick we used? All right, it looked like it's awesome. Okay. Right. So we provided this platform through algorithm A, and then now we call for any forger that is out there, come and play with us. We need your expertise. If you ever be able to solve this problem, then we are able to solve our hard assumption that we didn't know how to solve. So we need to go through some analysis for this algorithm that we've just designed. So the value of HIs. So the first thing first is that we said we have a random hash oracle. It means that the output should be uniformly random. And the truth is these values are uniformly distributed because we choose a random element Si from Zn, and then, by that, when we raise it to the power E, thus the value of Hi would be random. So therefore, the hash values as we expected are uniformly random. So every other signature that we generated for other than T is valid because we designed them to have this relationship, so they're fine. The forger is working under something that we call it carefully simulated environment. And it is because it is almost as what the forger would experience in a real time. So for that, we prove that this is like a real-time simulation. There would be some sort of different games that if we tell the forger to be a distinguisher, we let the forger to play with some algorithm that has the secret key D and generate the valid signatures, and then also the algorithm A that we generate that it didn't have the valid, it didn't have access to the exponent D, but he is able to generate valid signatures. So if the truth is we set up these two environments, and every other time we randomly choose one of these environments, the one that we have access to the exponent D or algorithm A, and then we let the forger to interact with them. At the end of the day, we realize that the forger can't tell if he's playing with A or he's playing with some real algorithm that has access to the exponent D. And if that sort of game we set up, then we can kind of prove that it is indistinguishable, because at the end of the game, we run it many times. So we count the probabilities, and then you will see that the forger cannot tell if he's in a simulated environment, he's playing with algorithm A, or he's playing with some real, signature algorithm with access to D. But looking into this, we call it carefully simulated because looking into the values that the only way that it can tell is when he's interacted with this system. So the truth is the hash values that he received are uniformly random. If you run some statistic test, he won't find anything there. The signature are valid, so he wouldn't be able to find anything there as long as we take the good steps. Like, for example, we said that we randomly choose Si from Zn, as a signature. As long as we do a good job there and we sort of uniformly finding those values, then the forger wouldn't be able to tell if he's interacting with algorithm A or the real one. So why do we have to care about it? Because if it is really he can tell if he's playing with a simulated area or real one, is that the probability that the forger would provide the signature, forged signature, wouldn't change because he's playing with the simulated area or he's playing with the real environment, right? If you can tell these two environments apart, regardless of who is he interacting with, he's using his techniques to forge a signature. And this environment doesn't give him, he doesn't gain anything from, let's say, interacting with A versus real environment and vice versa. So then F is genuinely doing his work and providing the signature, the forged signature that he's supposed to provide us. We said that we said that for the forged signature that the forger would provide, M should be some MI that we have we have queried to the Oracle model before, and if he just provide us a forgery of some message that we didn't even query the hash function, so we know that for any of those for this forger to correctly even guess the output of the hash function is 1 over n, which is already negligible. We have a lot of possibilities, and how come that he guessed not only the signature but also the output of the hash function, right? That would look very odd. We hope that that is a point that the M should be queried, and then at least with the hash function, and then later he would be able to provide that signature. And if that is not the case, then there's a probability of 1 over n that is M could be valid, and the hash function is exactly what we were expecting for. So now suppose that we are trying to even be more realistic and saying that the answer of the other question, a student, that F might not be successful all the time, but sometimes it would be successful. So we call it the successful if he return a forgery, that the forgery is also valid for us, that we can utilize that to solve our hard problem. And then let's say that he would be able to do that and answer for some queries that the valid signature that we can utilize is 1 over r. You see that we choose 1t to be the index that we embed our hard problem, and then we expect that he answer we can embed our hard problem there, and we get the signature for that specific row. So we have r rows, and the probability of we chose the right t is 1 over r. So this is it is non-negligible probability that because r is not huge, so we should be able to do that. And also we assume that so that is the first thing by our construction. And then the second thing is that suppose that the winning probability of the forger itself is alpha, right? So F forger wouldn't win all the time, but with some probability alpha from 0 to 1, from 0 to 100, he would be able to solve with every interaction. Then that means that the success probability of the algorithm A is alpha over R, right? So alpha is if F wins, and then 1 over r, because we have to guess that exact row correctly so that we embed our hard problem, and that has the probability of 1 over r. So together the probability of A to win, the probability of A to win or to success is basically alpha to the r, right? This is the probability. So the thing is like how we can increase this probability. That is not our intention, but in practice, if this adversary F or forger F show up, we can basically run this algorithm many times, and that would increase the chance of winning, right? So if we run it R times, then for sure we would win one of them according to the laws of probability. Then the average we should win. That is the thing, that if somebody came up with this forger algorithm in practice, but the point is that is not our intention, because all we have shown over here is that we have the platform, and if somebody calls and says that I can forge the signature, then we can show that we can solve RSA problem with that forger, with interacting with that forger. And we already have the description and very concrete algorithm how we can do that. So after this, I think our conclusion is that as long as RSA hard problem is believed to be hard and we don't know how to solve it, then such a forger should not exist in the first place, because existence of such a forger, we show that with some non-negligible probability we can solve the RSA problem, and it contradicts our assumption that RSA problem is hard. So if you go back to the proof of the theorem under RSA assumption, we start our proof under this one. So, and then at the end we are showing that we are showing that if such a forger exists, then RSA assumption is no longer hard, right? So this contradicts, and then it means that the forger doesn't exist, right? So that's the conclusion that we would get. So therefore, the forger doesn't exist and our algorithm is secure. So this is the steps and the conclusion that we would get out of there. All right, so I hope that you enjoy this kind of proof. Security proofs are usually contains a lot of tricks, a lot of cheatings sometimes. It is not easy, so you need to read enough of proof of the crypto systems. In digital signature, we have some techniques. In encryption systems, we have some different techniques. So if the question is like how we can learn them, unfortunately, like in mathematics, you have induction or contradiction. So in induction, you have steps you can make to get to your proof. But unfortunately, as you can see, in crypto systems, we don't have very beside the reduction that we know what is the beginning and the end. So within that reduction, we need to have some steps, and as you could see over here, some cheating. These are just some techniques that you will be able to learn them after you read enough security papers, and you would get to know some of those techniques. But the truth is, when you want to come up with some new, let's say, digital signature, for example, it is not guaranteed that those techniques that people used before you would be applicable for your design. So a lot of time, cryptographers will spend a lot of time for the security proof, because you need to find a new technique because you're using some different design. You need to just be patient, read enough, and learn the techniques, and hopefully with what you come up with, it wouldn't take a long time, or it doesn't require a very extraordinary technique to solve it. Anyhow, so I hope that you get to taste the flavor of how a complete security analysis look like. So far we've been just talking about it, but I think this was the first time that we did at least a high level with some good amount of details that how it should look like. So now you understand a bit better of how things are going on. So later on, we would have even some more that we will go to the details together. So now we are done with that, digital signature with RSA and RSA crypto system. We discussed a lot about RSA. So RSA is not the only thing in the market. We have other encryption system and digital signatures. We are going to explore some of them here today. The first one that we want to talk about is El-Gamal encryption. El-Gamal is the last name of the cryptographer, the famous one, that he came up with this encryption system, and then he named it after himself, ironically. It's very common. We go through the description, and then we go back, and then we would have discussion that how it works. So the first thing first is that we have a key generation. So the first step is that we want to find a prime such that the prime, choose a prime P and a primitive group G where p minus 1 has a large prime factor. This is like a little bit different prime that we have generated comparing to what we've done before. So let me expand on this step number 1, how we can do so. So he says that he's asking that p should look like something like kq plus 1, right? Because if that is the case, then p minus 1 equals to k times q, right? And then we know that q is a large prime, right? So going back to the description where p has a large prime factor, so this is what we are looking for, because there's a huge subgroup, not a significant subgroup over here. So how do we find this p in the first place? So we don't start with p, we start with q. Actually, we do a trick. So find a large prime q, and then we would basically we would start with some k. We do kq plus 1, we test is prime or not. If not, we just continue. We do k plus 1, q plus 1, and then we do k plus 2, q plus 1, and then we continue until we find somewhere that k plus I times q plus 1, this thing is a prime. So therefore, or p equals to k plus I times q plus 1, right? So this way we guarantee that, this for loop, if you imagine, it wouldn't take long time to find. But what we would see is that then p minus 1 is k plus I times q, right? Q is a large prime, so then we would have probably 2 subgroups over here. If k plus I is not a composite number much, but we would guarantee that we have at least one large q that we were looking for. Okay, so that is what it's called, the step number 1. So and then the primitive, I think, or generator, I think it would be easy for you to now to understand and how to find it. So then the next thing is that we want to find choose a random number x, and then x has to be in the group zp minus 1. So that means that x has to be greater than 1 and less than equal to p minus 2. So you may wonder, why do we have to have this condition over here? Remember that if you take any group from zp, from x from zp, and then if we get x to the power p minus 1, which is the length of b, zp, the length is p minus 1, right? Then mod p, then this thing is going to be 1, right? Because we said that if you raise any number to the order of the group, according to the Euler's theorem, then this is going to be 1. So we are choosing this x as our secret key, and then we don't want our public key to become 1, because then everybody knows what is our x, right? So that's why we want to make sure that x is in zp minus 1, which is doesn't include the p minus 1, right? So then that this y never becomes 1, and that is the reason for that. So once we have done this computation, we can set our public key to be p, g, p is our prime, g is our generator. Everybody should have the same generator to work with. And then y is our g to the power x. And then the secret key is just g, p, g, and x that we had before, right? So I think remember that here we are talking about the discrete logarithm problem. So it is okay for us to publish this value with everyone, because given p, g, and y, right, it is computationally hard or difficult to find x such that g to the x equals to y mod p, right? This is the discrete logarithm problem. If you publish your public key, nobody should be able to drive the x because this is the discrete logarithm problem. The best known algorithm we have is to just iterate over this value. So, or p is large, there are like millions, billions of numbers to iterate over. So we know that it's computationally very difficult to find such a thing. So that is given. Then the rest is okay. Now we have understood the key generation. We know that there is no risk to publish the public key. It is secure under discrete logarithm hard assumption. So now let's look into the encryption and decryption. In order to encrypt the message under this public key and the message M, we would do one thing. We generate a random number K. Sometimes you just use R, but over here we just started to use K. So you find a random element from ZP minus 1, so it could be from 1 to P minus 2. And then we do this computation, G to the K, and then Y to the power K multiply to M. So the interesting thing over here is that, as you could see, unlike RSA, it is already a randomized algorithm because every time you want to encrypt a message, you have to generate a new random value over here, right? So if I want to encrypt this message for the second time, because of this step, I might take a different K, and that means that the resulting ciphertext could be totally different, right? And then the decryption is very simple. So we treat the first part as A and then the second part as B, and then we just do B divided by A to the X. Well, this is the textbook description of how you look into this. Well, again, we don't like the textbook description. So let's see how it works. Let me also change my pen color. Okay. In order to encrypt under public key some message M, we said that what we want to do is that first thing first is we generate a R. I would start to use R. We randomly choose an R from Z P minus 1, right? So I'm using this notation R over here means that randomly. So this is an important step. You always want to choose this one randomly. So in order to compute the ciphertext corresponding to this plaintext, so what we do is that we compute G to the R mod P, and then also compute M times Y to the R mod P, right? So let's see what actually we are computing over here. So the first one is just like G to the R mod P. And then the second part, if we really look this closely, Y is our public key and Y we computed to be G to the X, right? So we are doing M times G to the X multiplied to R, right? So G to the RX, that's what we are computing, mod P, right? So this is interesting that, we are computing these values and then sending them over the ciphertext. But the question is that, does it really hide my message? Because I'm just multiplying my message to this value, which I randomize it. And then the question is yes, because since R is random, then it means that G to the R mod P is also random, right? So P is fixed, G is fixed, but R is different, so G to the R is also random. So then it means that G to the R can hide our message M, right? So this is the only place that we are hiding our message. Everything else is fixed. But you can see that G to the R is the one that is really hiding our message, the R. So that's why I emphasize over here that you really need to take a random R as input over here. So how does decryption works? Why are we able to do the decryption? So the decryption SK, given the secret key, and then we receive two elements. We call them A and B. We said that it is equals to B over A to the power X, right? But let's see, what do they look like? B is basically M, let me replace them, M times Y to the R, right? And then what is A? A is G to the R, so I would write it G to the R, and then when you multiply it to X, when you raise it to the power X, then what we get is basically MYR and then GRX, right? And if you look closely, then what we have here is that MYR, G to the X is basically Y, right? According to our public key description. And then you're raising that to the power R. So it's easy to see that these two would get cancel each other, and then we get our message back, M, right? So the decryption is very easy. So the only thing that also sometimes the students would, they often make a mistake is that notice that I want to put a notice here that G to the X times G to the R is not equal to G to the XR. Sometimes people say that, well, I have this G to the R, but if I multiply it to this G to the X, which is my Y, I should already get this one, and I can decrypt this message. Because this part is G to the X plus R. If you just multiply it, it is not, or G to the XR that we are looking for, right? So in order for somebody to decrypt, you really need to have X, so that you raise X to the power A, you raise A to the power X, and then you are able to decrypt the message. If you multiply A, which is G to the R, to G to the X, which is the public key, you get J to the X plus R, not J to the XR, right? So then you really need to have this X in order to decrypt this crypto system. All right, so that is given. So I hope that is clear. So what is the security problem that we are talking about here? So the security problem here is as following. I'm saying that given P, G, Y, which Y is G to the X, and then G to the R, and then M to the YR, right? These are the piece of information that I'm having. I'm I'm asking you to compute M. What is M? So I'm giving you all this piece of information: the P, the generator G, the Y, which is the J to the X, because I have this because it is a part of the public key. I have G to the R, it is the first part of the ciphertext, and also M to the YR, which is the second part of the ciphertext. So these two together are the ciphertext. And then I'm asking you to compute M, okay? And this is the security problem that we are dealing with for the LGML, problem. For the proof and different things, we will talk about it later. But before we go further, I wanted to show you that. Let me see, how much time do we have? Oh, it is 40. Okay, so maybe I'll stop here because this one would take quite some time. So we wanted to just, let me write it down so that we know what we do next week. So that LGML encryption is not secure against chosen ciphertext attack, or CCA. Just like RSA, it is not secure against chosen ciphertext attack. So I think this would be the discussion that we would have next week. So for now, we would just stop here. Let me see if there's any questions. Do we have any questions? All right. How can I know the error in homework 1? Well, the point is, homework 1, I published the solutions. You should be able to download it from EE class platform. You have access to the reference solutions. And if you think that there is any mistake in counting, or you think that your solution is also correct, it was graded with some errors, please contact the TA, and then he would help you to deal with that. Okay. All right. So looks like there's no other questions. We'll see you guys next week.